Welcome back to our 5th Flownex online training session. In this session, we'll look at the different ways to model flow restrictions. And I'll give you guys your first Flownex exercise to perform on your own time. So let's start off by asking, what exactly is a flow restriction? Well, actually any component that conveys your fluid, except for pumps and compressors, is also restricting its ideal flow. Pipes, vents, valves, orifices, heat exchangers, even turbines. Now, obviously, some are used deliberately to control or restrict our flow, such as valves and orifices. But in theory, all of them can be represented very similarly. Let's have a look at that. For a straight pipe section, the pressure loss is calculated by delta P equals FL over D times a half rho V squared, which also gives FL over D multiplied by a half mass flow squared divided by density and area squared. By attributing all the geometry related variables to the flow resistance, we can now say that delta P equals the flow resistance multiplied by mass flow squared divided by density, where the resistance term is FL over D times a half divided by area squared. For a specific pipe, the resistance is therefore a constant or fixed value, giving that for a constant density, the pressure loss will exactly follow a quadratic relation with increasing mass flow. Let's look at an orifice. Here, the pressure loss can be calculated using delta P equals K times a half rho V squared, where K is termed the loss coefficient. So the resistance term is K over area squared in delta P equals K over area squared multiplied by a half mass flow squared divided by density. In this case, however, the resistance term is not a fixed value as with the pipe, since K is subject to several variable fluid properties, such as the Reynolds number. So here, the pressure flow relationship is not purely quadratic, but will deviate depending on the geometry. The same also holds true for components with intricate geometries, such as valves or heat exchangers. Now, why am I telling you all this? For simulation purposes, we can actually model any component that conveys your fluid, except for pumps and compressors, with a single component with some kind of adjustable pressure flow correlation input. So we can then model pipes, valves, sudden expansions, you name it, with just this one tool in our software. Are you following me? But that would have been quite boring and might even get confusing as to which is which on the plant. So, we've created a whole spread of different flow restriction components in Flownex, each with their own relevant inputs. But always remember that they are all doing exactly the same thing in theory. So you can model an actual valve with some restrictor component, or even an actual pipe using a valve with a quadratic pressure flow characteristic. Got that? So let's quickly go through some of them. You've already seen the pipe, but I want to introduce you to our database for selecting the diameter from different pipe standards, roughness for various pipe materials, and secondary losses, like a specified amount of, say, 5 90-degree bends. For detailed modeling, you can use either of the pipe bends, specifying the bend angle and radius, and also the flow distributors, such as T-junctions. But as a general rule, I would like to point out that the effect of detailed modeling of bends and junctions are negligible in comparison to the rest of the system, and it clutters up the system layout on my screen. So in 99% of all cases, I personally use the secondary loss input in the pipe to include the approximated effects of bends and junctions. We furthermore have an orifice with required inputs for the tapping specification, pipe diameter and orifice diameter. Generic restrictor with loss coefficient component with required inputs for the area or diameter, the contraction coefficient quantifying the vena contracta effect, and the loss coefficient. The restrictor with discharge coefficient, which is a simplified version of the previous one and is to be used at the outlets of pipelines to atmosphere or large reservoirs, as well as pipeline diameter adapters from the Crane, Idleschick and Miller textbooks. Under custom losses, we have, amongst others, the general empirical relationship, which requires values for CK, alpha and beta according to the relationship delta P equals the coefficient CK multiplied by the density to the power of beta and volume flow to the power of alpha. For general purposes, you can use a value of 1 for beta and 2 for alpha, which will give you a quadratic pressure flow relationship. And then my personal favorite, the flow resistance component, which only requires one input, the flow admittance. This value is the inverse of flow resistance. So it can be written in the form delta P equals 1 over admittance multiplied by mass flow squared divided by density, giving that a larger value of admittance will give less pressure loss and a smaller value will increase the pressure loss. There are also discharge nozzles, inlets, and then a whole set of valves, which include generic valves with different functionalities and different levels of detail required to their input specification, as well as our set of custom generated valves from the Miller textbook that represent the individual characteristics of several specific designs. Now, with the knowledge of all these tools to your disposal, I want you to try and model the small system shown on the screen. You can pause the video to take a good look at the problem specification or even take a screenshot. And if you've forgotten any detail about the use of boundary values, pump design or flow restriction components, you can go back and have a peek at the previous sessions. In our next session, I'll take you step by step through the process of setting up this network, or at least how I would have done it anyway. So prepare to start solving the world's biggest thermal hydraulic problems. And until next time, goodbye.